Hi guys! Welcome back. Now in today's video, we are just going to revisit the concept of the
Shuttler's
principle. So in last week's video, we did mention to you how concentration was one of the stresses. Now today we're going to build on this and we have 4 more stresses for you guys. Now the first one will be changes in pressure,
introduction to inert gases,
catalyst,
and temperature.
Alright, now let's visit the first one, which is pressure.
Alright, okay, so again, we have this system set up here. We have a reversible reaction between PCl3 and Cl2 to form PCl5. Alright, now what we're going to do is this. We are going to increase the total pressure of this entire system. And recall from your gaseous state and how we do that. We can perhaps decrease the volume, but I won't go into it. But anyway, we're going to increase the total pressure of all the entire system. And remember what we have learned in the Shuttler's principle. Your stress is always this vertical increase. Okay, so you can see partial pressure against time. This vertical stress here is your vertical increase, is your stress. All right. Now, Mr. William, we're going to be a bit careful here. When I increase my total pressure, my system will try its best to respond to this stress, and this change will be reducing the pressure, right?
Yes.
So help me out. Which POE should I favor, left or right, to reduce pressure?
Well, to answer this question, you must realize that pressure is proportional to the number of moles of
Right,
gases.
okay.
Right, so the very first thing that we're going to do is we're going to check out the number of moles of gases on the left-hand side and the right-hand side of the equilibrium.
Okay.
Right, so we can see on the left-hand side, there are 2 moles of gases, which means left-hand side is going to give us higher pressure, whereas the right-hand side, there's only 1 mole of gas, which means there will be lower pressure. And what do we want here? We want lower pressure, right, which means the position of equilibrium is going to shift towards the right-hand side.
Okay, so if the POE shifts to the right, then it's quite intuitive. You will realize that the partial pressures of PCl3 will clearly drop, and Cl2 will clearly drop, and the partial pressure of PCl5 will definitely rise. And again, right, your response is always this gradual change, right? So you would see PCl3 decreasing gradually, Cl2 decreasing gradually. I should use a different color, my bad. All right, and the PCl5 should increase, but gradually. Okay. Now again, you will realize that after a while, at time 2, this is where your partial pressures of each gas becomes constant with time. You can see how it is fixed again, fixed. That means the new equilibrium has been attained. And again, just remember, we are not changing temperature here. So the initial Kp and the final Kp at T2, they must be the same. Okay, and this is basically what pressure is. Not too bad, not too bad.
Okay guys, now we're going to take a look at how inert gases is going to affect equilibrium, which I feel is one of the most difficult concepts for students to master. Right, usually in the introduction of inert gases, there will be 2 conditions. Right, I'm going to run through the first one. As you can see from your notes, is when the volume is going to remain constant. Right, now we do have an equation over there, which we're going to make things even easier by showing you there's a container or a box on the left-hand side. Now we're just going to zoom into this. Okay, let's make an assumption. Okay, let's assume that this equilibrium only comprises of gas A as well as gas B. Alright, these guys are in equilibrium and they're in a container right now. So what's going to happen, they're going to move randomly and they will collide against the wall and they're going to have a pressure, right? So let's say, I'm going to say that the P total of this container is going to be 20 atm. 10 from each. Okay. Right. And what's going to happen right now is I'm going to introduce an inert gas. So the inert gas is the one in black, right? So this guy's going to enter the system. Okay. So now that he's in the system, will he give rise to some pressure?
Of course, because he'll bump into the wall too, right?
Yes. Okay. So let's assume he's also going to give us 10 atm. Okay. So what's going to happen to the new P total? Alright, now the new P total is going to increase to 30 atm, right? So quite clearly, you do see that there's an increase in P total, which leads to the confusion because some students will think when P total increases, the system will start to shift. Okay, but the key thing that we must be mindful of is who is part of the equilibrium and who is not part of the equilibrium, right? Yes, the P total has increased, that's without a doubt, but you must be mindful that the inert gas is an inert gas and it's not part of the equilibrium, right? So as far as the equilibrium is concerned, your focus should entirely be on A and B and totally disregard the inert gas.
For sure.
All right? So what will happen is, imagine A and B will continue to bounce off the walls at the same rate, right? So, Mr. Tim, even though the inert gas is there, and bearing in mind gases are widely spaced apart, our picture is not accurate representation. Now, will A and B's bouncing be affected by the presence of inert gas?
I don't think so. You still bounce at the same rate, right? Frequency. So I don't think so.
Exactly, right? Because you have the same number of moles, you have the same volume. So you must accept that even though there's another gas inside, the rate of bouncing of A and B doesn't change. What does that mean? It means that the pressure of A and B, which is part of the equilibrium, is totally unchanged. All right? So you can see, let's just minimize this a little bit, right? The total pressure may have increased, but the partial pressure of each gas, keywords, in the equilibrium, right? In the equilibrium is unchanged. So long story cut short, nothing happens and there is no real need for the equilibrium to shift in this case.
Easy.
Okay, now let's just step up a little bit. Okay, what if the total pressure remains constant?
Now this is where things are going to get a little bit more hardcore, but again, we are going to use this diagram here at the bottom to explain this. So like what we were saying just now, right? We have A and B, part of the equilibrium, okay, and then we're going to introduce this inert gas I into this equilibrium, and like what we discussed, the total pressure will increase from 20 atm to 38 atm. Now you can see I'm quite sad here because I don't want the total pressure to go up, right? Because this condition is the total pressure remains constant. So now what I need to think is this. Now Mr. William, if I want to bring down my total pressure back into 20, which means I want my gas particles A and B now to bump onto the wall less frequently. Now how do I do that?
Well, you will have to increase the volume of the container to
yeah.
ensure that their individual pressure is going to drop.
Okay.
And once it drops, maybe that 30 will return back to 20.
Exactly. Alright. So we will increase the total volume of the box so that the partial pressures of A and B is now reduced because now it bumps on the walls less frequently. So instead of the 10 atm of partial pressure at the beginning, now perhaps it's 6.
Yeah, just some
20 divided by 3. Okay? So now it's basically reduced. So understand with me, you are now changing the partial pressure, like what we said, of A and B that is in your equilibrium. So because the partial pressures of A and B in the equilibrium is now decreased, you would definitely shift the POE. The shuttles will definitely kick in, right? Because you're applying that stress. And yes, again, their POE will shift to the side with a greater number of gaseous species to again increase that partial pressure, right? So there we have it.
So I think in summary is you must be very clear, not all gases is part of the equilibrium. The focus is to really touch on the gases in the equilibrium. Are they affected or not? If they are, then the equilibrium will respond.
Correct.
Okay guys, now we're going to touch on the third stress, which is the addition of catalysts. So Mr. Tim, you know, what does catalyst usually do?
Well, it reduces the area of the reaction, right? And then it speeds up the whole reaction.
Yes, so things get faster, right? So when things get faster, then you expect the rate of reaction to increase as well, right? So if you take a look at your graph, there is a graph of concentration against time, right? So we can see the first graph is the one without a catalyst. Now, without a catalyst, it will take 4 minutes for us to reach a state of dynamic equilibrium, right? And with a catalyst, what has happened is we will lower the time frame it takes for us to reach the same spot, right? So you must be mindful. It doesn't change Kc, so the amount of reactants and products is still going to stay the same, but it's really the time that it takes to do so, from the original 4 minutes to now 2 minutes. And as what Mr. Tim has mentioned, you will also lower the activation barrier. So you can see this is for the uncatalyzed reaction. This is the barrier, which I like to call as the mountain to climb. So we have a huge mountain to climb, and once you add a catalyst in, what will happen? You're going to lower the mountain to climb, and therefore the rate of the reaction will increase. That's what catalysts do.
Alright, so guys, we're going to look at the last stress, and that is temperature. Alright, so what I have for you here is yet again a reversible reaction, CO plus H2 becoming CH3OH. Alright, now take note, this reaction, the forward reaction, is actually exothermic, so we have a negative enthalpy change there. And yes, what we're going to do is this. When equilibrium has been established, we're going to stress this equilibrium by increasing temperature. Now again, so think about this with me, right, Mr. William? If I'm going to increase my temperature, then my system hates this, right? It will respond by reducing my temperature. Can you help me out? Which POE should I favor, left or right, to reduce temperature?
It will favor the endothermic reaction,
okay,
because you want to absorb the heat in.
Right.
And delta H is always with respect to the forward reaction, right? So if forward is exo,
and the backward must be
endo. Yes.
Fantastic, right? So to reduce this temperature, then I would favor the reverse reaction because that's endothermic, forward is exo, and there you see it. We will shift to the left, right, to absorb the heat, favoring the endothermic reaction. Now, this is the part that I want you guys to pay a bit more attention. Yes, when you favor the endothermic reaction, so again, your reactant concentration, they will go up, and your product concentration will go down. Now listen, this is the only time where Kc is affected. So when we talk about catalyst, when we talk about pressure, talk about concentration, it never affects Kc. Temperature is the only one, and write this down with me, that affects your Kc. All right? So last thing before we move on, if after my POE has shifted to the left, right, I have more reactants now and less products. Could you help me out, Mr. William? How does my Kc change then?
Kc is going to decrease because you're going to shift the equilibrium backwards.
Of course, okay. So Kc is always product over reactant. I got less product now, more reactant now. My Kc will definitely fall. Now we're going to take things up a notch. What if my forward reaction was actually endothermic and I tried to decrease temperature? Now, Mr. Willem, bring me through.
Okay, sure. So I'm going to bring you guys through the flip side of a coin, right? So as what Mr. Tim has mentioned, this is an endothermic reaction. Okay, I cannot stress how important this is. This is always, I'm going to write this here, with respect to the forward reaction, right? So what it means is the forward reaction is now going to be endothermic in nature, right? So we revisit that thought process of you stress it, there is a response, and there is an outcome. Okay, so what is the stress right now? Now the stress is you're going to reduce the temperature, right? So to reduce the temperature, there's a stress. The response will be the exact opposite. You want to increase the temperature, right? So to increase the temperature, what's going to happen is you're going to favor the exothermic reaction, right? So this is what we call the response, right? The response is simply trying to increase the temperature, favoring the exothermic reaction, which, bear in mind, it has to be the backward reaction, right? So in this case, if the response is to shift backwards, then we are going to expect more reagents and less product. And remember, Kc is always the ratio of the products divided by the reactants. Since there are now more reactants and less products, then mathematically speaking, what's going to happen to Kc? Kc is going to drop, right? So you have to explain this is going to be the outcome, right? So the outcome is you have less products and more reactants, and Kc is going to be affected, right? So remember this, temperature is the only stress that can affect the value of Kc, right? So as a summary, this is what we have explained to you. What happens if there's an increase or a decrease in temperature? Just think opposite, right? We're trying to relieve the stress. Okay, I think it's getting hot.
Yeah, let's relieve our stress.
Okay, we'll see you in class. Bye.